Alright, welcome everybody. Today, in this video, we're going to talk about statically indeterminate problems. And from statics, as a prereq for this class, you learned all about statically determinate problems. A determinate problem means that we have enough equations for the number of unknowns we're looking for. Typically, in statics, we have some of the forces x equals 0, some of the forces y equals 0, some of the moments equal 0, so we can have up to 3 unknowns. Well, the nice thing about strengths is it allows us to develop another equation or two in order to solve some more complex problems. Now, the way we're going to solve these, they're all going to be based on this idea of superposition. So let's start with defining what I mean by the principle of superposition. So the principle of superposition basically states that everything is linear, and because everything's linear, then we can take things apart and put them back together. Or if I'm going to define this, what I would say is that all of my deflections, forces, and stresses can be linearly added together. So, for example, if I had some kind of column, and let's say this column had 2 forces on it, we'll have a force pushing straight down, we'll call that FB, one pushing up, say it's some of the midpoint, FA. When I'm analyzing this structure, I can break it into 2 different parts, one from the force at A and one from the force at B. Something like that. And because I can break it into these 2 different problems, I can analyze it in a cool way, which we'll see in just a second. I do want to point out that this only works if everything is linear between our deflections, forces, and stresses. So the whole thing falls apart if we're outside that linear elastic region, or if you have very large changes in the geometry, like if you had a material that's getting very skinny as we stretch it, or if you just have a nonlinear material. But in this class, for the rest of this semester, it'll hold true that that our deflections, forces, and stresses will be all linearly related, and we can use this idea of superposition. So let's look at an example of how I would use it to solve a statically indeterminate problem. So in this case, what I have is this 20 kilonewton force P that's pushing on this collar that's attached to this AB, and AB is held between these 2 rigid surfaces. I'm given that it's a steel bar and it has some kind of diameter of 10 millimeters. And what I would like to do is I would like to find the reactions at A and at B. So looking at our statics and drawing a free body diagram, what I would see is something that looks like this. So the reason this is statically indeterminate because the only equation that I have is sum of the forces in the x direction equals 0. From that I get that there's a 20 kilonewton force pushing forward, and resisting that force are my reactions at A and at B. I can't do anything in the y direction. I can't do any moments. So really what I have is 2 unknowns and 1 equation. So we have a name for this. This is called statically indeterminate to the 1st degree, or we have 1 redundancy. So that's our first equation that we can have. It is only 1 equation. We need a second equation. We can use strength of materials for that second equation. So the way that I'm going to do this is I'm going to break this bar into 2 separate pieces. So to help me label this thing, I'm going to say that this is A on one side, B on the other, and then we'll have this little C at the collar. It probably makes sense anyways, but breaking it apart, this is what my little section AC looks like, and slightly longer section. Looks like I'm growing on this whole thing for whatever reason, but this is section AC and this is CB. Now with both those parts, I have both of these would be, or actually, sorry, take it back. The one on the left would be in tension, and it would be in tension by the magnitude of FA. So it's like we're breaking it just right before that 20 kilonewton load is applied, or what I'm just looking at is the overall tension in A to C. And if I were to cut it anywhere in here, method of sections, what I would see is there has to be a tensile force of that reaction. On B, same idea, but on B I'm in compression. And once again, if I were to break it anywhere in here, I would know that some of the forces in the X would mean my internal force would be that axial reaction at the end. What I know from this idea of deflection, or how much the member is going to either compress or stretch, is that we're given the deflection at C. Now I know A is rigid, right? A is not moving. So C is the only direction that can move. And I know how far it would move. It's equal to FL over AE. So that looks like what we've seen before. Before we were calling it PL over AE, but it's the same idea. Just putting in my variables. Instead of a P, I have a force at A. Instead of a length, I have LAC. Area and E are the same for both cross sections. So I'm not really doing too much with that. Now on the other side, I have part B is against a rigid surface, so C is the one that would move. Once again, it would have to compress, and that would be equal to the force at B times the length of CB over AE. So what I end up with is these two equations for C, for how far C is moving, and C can't come apart, right? So the collar moves a certain distance to the right, and it has to move the same from AC and BC. So because I have these two that are equal to each other, we know that our delta C must be equal delta C. We have a name for this. We call this our compatibility condition. Basically, compatibility condition means in order for this problem to work, or for it to exist in real life, that has to be, C has to be compatible from the right hand side and the left hand side. So that means I can set these two equations together and I get equal to each other, and I have this relationship between the two. Now the cross-sectional area is the same in both of them, and they're made out of the same material, so that A and E actually cancels out. You could see how that would also affect the reaction at both sides. So putting in my values, what I end up with is, let me move the length. So it's really just a relationship between the lengths, right? So I have length of CB over length of AC times FB, just doing a little algebra. And then I have that length of CB is 800, length of AC is 400, FB, or what this gives me is that the force at A must be equal to twice the force at B. So this is a second equation. We already had our first equation up here, right? Now we have a second equation down here. We have two equations, two unknowns. We can finally solve this thing. So what we're going to do is we're going to sub this into our equation 1. And if I do that, equation 1 said that we had 20 kilonewtons minus FA minus FB is equal to 0. Or what I can say now is that 20 kilonewtons minus 3 FB is equal to 0, or FB is equal to 6.67 kilonewtons, and the reaction at A is twice the reaction at B, which is 13.33 kilonewtons. And I don't know if that would actually make intuitive sense to you or not if you went back to the original problem and said, you know, I'm applying this collar, everything else is equal, and I'm applying this collar right here, force on this collar of 20 kilonewtons. Which side would take more of the load, side A or side B? And it ends up that side A, the closer side, everything else being equal, meaning material and cross-sectional area, side A actually takes more load. How much more load? Well, oh my. I just realized from the very beginning of the problem I never gave you the dimensions of these two, did I? So you're probably like, what's going on? This side was supposed to be 400 millimeters and this side was supposed to be 800 millimeters. Oh, fonts, no. But since I'm too lazy to re-record this, I'm just going to stick it in there and assume that you'd be able to back figure this or look at this problem again. Anyways, the point being is that if I'm putting this load on here of the 20 kilonewtons and I'm closer to side A, I'm like twice as close to side A, I'd have twice the load. So that's the whole thing is based on this principle of superposition. I hope my fan from my computer isn't too loud. It sounds like it's about ready to take off over here. Another way we can look at this, it's actually the exact same problem, just a slightly different method. And this alternative, I'm going to call this the force method. So let's once again take a look at this problem. And what I had was, between these two rigid supports, I have a force on this collar that's equal to 20 kilonewtons. I'll ignore drawing the collar to save some time. This is point A, this is C, this was B. Now we know that this distance is, don't forget that again, we'll make that mistake again. I already forgot, what were they, 4 and 800, yep, 400 and 800, or the whole thing is 1200, right? Well, the way this force method works is, that's my initial problem, and the first step is I'm going to remove a redundancy. So like I said, that is a statically indeterminate to the first degree, meaning I have one redundancy. Well, I'm going to remove that redundancy, and the redundancy that I'm going to move is the reaction at point B. So if everything else is the same, I still have this pulling at 20 kilonewtons, and I remove the reaction at B, then I know that this whole thing, as we've seen before, would elongate. I'd have a little bit of a delta here, right? I'll call this delta at point B. So this first step is to remove our redundancy, basically making it statically determinate, right? And then the second step would be to apply a force, that's what we call this, a force method, where we remove that redundancy. So I'm going to apply a force over here. This is my force at B. And if I apply a compressive force, now notice I'm not putting the 20 on there anymore, just that compressive force, this whole thing would shrink back down a certain amount, a negative delta B. So the second step is apply a force at the redundancy and apply this idea of compatibility. Well, in this case, what is compatibility? Compatibility is saying that our total delta at B, however much it grew in the beginning, plus this, how much it shrank in the end, must be equal to 0. Because I know that the wall over here, the physical constraint, actually doesn't move. It's like, theoretically, if I didn't have that wall there, how much would it grow? How much is the force pushing back? That is my reaction at the end. Now this may look more difficult than the one that we just did, or the other method, but really they're based on the same principles. Sometimes this method will be much easier depending on your problem. Sometimes the other method might be a little easier. I'm a bigger fan of this force method, and you'll see me use that quite a bit. So let's see how I would do the rest of this. For that first step, we know that the delta B would be equal to our PL over AE. So I'm applying a 20,000 Newton force over a length of 12. Sorry, oh, I almost screwed up. I almost made a common error. For this delta B, if I wanted to know how much it's going to actually grow here, and I have this PL over AE, the length that's growing is only this length from the support out to point C, meaning the rest of this, the whole rest of this section up here, there's no force on it. So that part's just kind of going along for the ride. So the overall length here is 400 millimeters. It's not the 1200, but only the 400 is the part that's actually growing in length. Hopefully that makes sense. Look at it. Where that collar is applied, to the left is the only part that would be being stretched. Cross-sectional area, pi over 4, 10 squared. This one I'm putting in the area, so I need to know that diameter. E for steel is 200,000 megapascals. If I plugged all that in, I end up with 0.50929 millimeters. So that's my total change in length if I removed my redundancy. For that second step, what we're saying is our deflection at B afterwards, so this would be like from 2, maybe I could label this as 1 and 2, right, is equal to the force at B times the length over AE. So this reaction at B is what my unknown is. Now, when I'm looking at compressing this whole thing in, it is the entire length. So that's the entire 1200 millimeters over the cross-sectional area, pi over 4, 10 squared times 200,000 megapascals. And I know that this whole thing must, because of this compatibility, must be equal to this 0.50929 millimeters. Those are rigid supports. So I'm just bringing that straight down and saying that is my compatibility condition. Solving for my reaction at B, and I get the same thing that I got up above, 6.67 kilonewtons. And I can do, then I can go into the fact that I know that my sum of the forces in the x direction must be equal to 0. So I have a total of 20 kilonewtons minus the 6.67 kilonewtons must be equal, or sorry, plus my other reaction. Oh my, trying to go too fast here, making mistakes. It's equal to A, so my reaction at A is equal to the same thing I got before with this 13.33 kilonewtons. So that is the force method, just another use of this principle of superposition. Hope you found that helpful, and I'll talk to you all next time. Thanks.